Hi, welcome back to example 2 and 2.5 stretches of functions. In this example, we are to take each function, g of x, and describe the transformation from a base function, f of x. So those are our options for base functions. Then transform the graph of f of x to sketch the graph of g of x. So we're told g of x equals 3 in the first one, and then in b, we're told it's equal to this one. So if we're to start with part A, which we will, we want to see which base function corresponds to this function here. So g of x is basically taking one of these options and it's doing a transformation to it to get this. So I can tell by the form of this. I don't see any squares, so it's not this one. I don't see any roots, so it's definitely not this one. And it's not even in the form of 1 over x, right? Or 3 over x, so it's not this one. It looks a lot like the linear type. It's just 3x, so it's linear. So we can say uh, g of x equal to 3x represents a transformation to f of x equal to x. Okay, so this is our base. Okay, we're going to do a transformation to get this here. So we first got to describe the transformation. So there's two ways to look at this. So if you think of g of x as, let's say, 3 times f of x, so 3 times the base function in order to get this, then you're looking at a vertical stretch by factor of 3. Vertical stretch by factor 3. Okay, I know it's factor 3 because I can see this is my a value, right? This means a is equal to 3. So because a is greater than 1, it's a vertical stretch by factor 3. The other way we can look at this would be to think of it a little bit differently. So this g of x equals to 3x. What if I think of it in terms of a horizontal shift or compression? So what I mean by that is think of g of x as f of 3 times x. Okay. So notice f of 3x, that means I would have to switch x in the base with 3x. So this would go here and I get 3x. So that's another way to do it. And if you look at it that way, well, this actually means we have k equal to 3. So if k is 3, if k is greater than 1, we know we have a horizontal compression. So it says think of this as a horizontal compression by factor 1 over k, 1 over 3. Okay, I like to add these little quote marks to the factors. So that's two ways to look at this one, and we'll see that both are going to be correct. So I'm going to graph the base function. We'll get the y-axis over here, and we'll put the x-axis over here. So y equals x. We'll do this in black. It's going to go through the origin. And now we're going to apply the transformations to get g of x. So if we take this first approach to think of g of x as 3 times f of x, that means we're gonna look at this as if it's a vertical stretch, and a is 3. So If we do that, we have to multiply all the y values by a factor of 3. So we don't need to set up a table of values. We can kind of just do this visually. So we'll do this one in blue. So here I have the point 1, 1. Well, if I multiply the y value, because there's a distance of 1 here, if I multiply that by 3, my point ends up becoming up here at 3. So I'll mark it off on the y-axis just so we can see that a little bit better. Okay, so this distance here got multiplied by a factor of 3, so we went from 1 to 3. Now we have 2 here. If I multiply 2 by 3, I get 6. So my new point has to be at a height of 6. That would be right here. Okay, now let's talk about the origin for a second. At 0, 0, when you multiply the y value by 3, it still stays 0, 0. This is an example of an invariant point. So I got 3 points. This is perfect just for throwing a line through. So we can do that like this here. Okay, and this is g of x. And I did this by doing a vertical stretch. Okay. Now you might say, okay, well, what happens if you do it the other way? Like when we said to think about g of x as a horizontal compression. So when you see this equation here, g of x equals 3x, we first looked at it as a vertical stretch. We were thinking like if the 3 was outside being multiplied in. Well, what if we look at this as a value of k, and meaning we replaced x with 3x? So if we have a horizontal compression of 1 over 3, that means we need to take the y values, we need to take the x values, we're going to multiply them by a third. So meaning when I am at 3, notice here, when you're at 3, and if you multiply it by a third, it's going to bring you to 1. Okay, so that's the scale factor there. Likewise, if you're over here at 6, this is the point, it looks like it's at 6, 6. Okay, that has a distance of 6, obviously, from the y-axis. Well, if you divide that by 3, you're going to get a distance of 2 now. Okay, so there's the two ways of looking at this. Taking a linear equation and stretching it vertically is the same thing as taking that same equation and compressing it horizontally. It has the same effect. Okay, now we're going to go ahead and do this for the next one, g of x equals 4x squared. So g of x equal to 4x squared. So I know that this is related to the base function, f of x equal to x squared, okay? Because I can see the exponent in it. It has to be this one for the base function. So all right, let's go ahead and let's talk about the two ways that we can think about this function. So if we think of g of x, if we think of this as a vertical stretch for this one by factor 4, so if we think of it as 4 times f of x, then that would imply that we have a vertical stretch by factor 4. And then the other way to look at this, we could actually see it as a horizontal compression. So if you think of g of x as f of 2x, then that would indicate a horizontal compression. by a half. We'll say by a factor of half. Okay, so how does this work? How does this give us this here? Okay, well remember, if you take 2 of x and you replace that inside of here, so replace x with this 2 of x, you're going to have 2 of x squared. Okay, and 2 of x squared, well, we have to square the 2, and we can square the x. So that's another way of arriving at this. So either we think of this as a equal to 4, and we have a vertical stretch by factor 4, or we think of this as k equal to 2, and we have a horizontal compression by a half. And we'll show graphically that these are the same. Okay. Actually, let's move the y-axis over for this one. Right there. Okay, because we need to keep the center because we're working with x squared. So we have points here. This is our basic parabola, 0, 0, 1, 1. Then we have 2, 4, negative 2, 4. And we even have 3, 9, which we could get in here too as well. 3, 9 and negative 3, 9. So there's the base function, f of x. Okay. And now to get 4x squared, we can do a vertical stretch by factor 4. So that means you got to multiply the y values by 4. So if this has a distance of 1, when I multiply this by 4, I end up getting a point at 1, 4. Notice I now have a distance of 4. This one's at 4 from the x-axis to this point. If I multiply it by 4, I'm going to get a total height of 16, which I can't get in this graph. I only have 4 and then 8. Yeah, it won't even be able to fit. So let's go ahead and get a few more points. So we know the origin is going to stay because 0, 0, you multiply 0 by 4, you still get 0. Negative 1, 1 is going to become negative 1, 4 because you multiply the y values by 4, right? So just so we're aware, when we're doing the vertical stretch, we're thinking of x, y, we're basically turning it into x comma 4y, right? All the y values get multiplied by 4. So this is just going to look like a really skinny parabola basically because 4 actually is quite a big stretch. So that's g of x. Okay, we have these nice 3 points right here, so that's kind of good enough for us to do what we're doing. So if we look at this as a horizontal compression by a half, we'll notice like the points. This point is at a value of 2 for x, so meaning there's a distance of 2 units this way. Well, when we compress it by a half, we now have a distance of just 1. So the x values all get multiplied by a half. So this one, which is at a distance of 3, there's 3 there. Well, now we only have 1.5. So they all get bumped in by a half. So those are just showing you sometimes how transformations can be interpreted as 2 different ways and still be correct. All right, that's it for this example. I'll see you in the next video.